Somewhere above you tonight, there is a boundary in the universe that cannot be found by touching it, cannot be seen by crossing it, and yet decides before you even move which parts of your future are still reachable and which have already been sealed off forever. You could fall through one and feel absolutely nothing. No wall, no warning, just gone, mid-thought, into a future with no way back. Here is the part that should genuinely unsettle you. That boundary isn't made of matter, it isn't made of energy, it isn't even made of space in any sense you'd recognize. It's built from something far stranger, a single silent rule about which events in the universe are permitted to touch which other events. And a small number of physicists, working mostly alone and mostly ignored across most of the 20th century, proved something extraordinary, that this one bare rule is enough to rebuild almost the entire shape of reality from nothing, not an approximation, almost the whole thing. Once you see this structure, black holes stop looking like objects. The present moment stops looking like something the whole universe shares. And a 300-year-old argument between two dead men about moving the universe sideways suddenly has a real answer. Get comfortable. Hit subscribe if you're new here, because by the end of tonight, now is never going to feel quite so solid again. Now let's slowly ease into this. Part 1. The two things you have never once examined. There are two things you have used every single moment of your entire life, and it is almost certain you have never really looked at either one. You have wondered about plenty of other things. You have wondered whether there is life on other worlds, whether the universe had a beginning, whether the person sitting across from you sees the color blue the same way you do. Those are the questions people write books about, argue about at dinner tables, lie awake turning over in their minds. But every single one of those questions was asked somewhere. Every single one was asked at some moment. The somewhere and the moment came bundled in for free. They were never actually part of the question. They were the conditions that made asking a question possible in the first place. Space and time are the last things anyone thinks to interrogate, and the reason isn't laziness, it's structural. You cannot step outside space and time to get a good look at them, the way you can step outside a room to look at its walls from the hallway. Every measurement you have ever taken, every observation you have ever made, every single thought that has ever passed through your mind happened inside the very things we're about to try to pull apart tonight. When physicists tell you that space and time are the hardest problem in the entire discipline, this is a large part of what they mean. It isn't that the mathematics is especially brutal, although it can be. It's that the person doing the investigating is standing on the very thing being investigated, the way a fish would struggle to have a theory of water. So let's start small. Hold your hand up in front of you right now, in the dark, in bed, wherever you're listening to this. Spread your finger and your thumb apart until there's a gap of maybe 10 centimeters between them. Now ask yourself a question that sounds too simple to matter. What exactly is in that gap? The obvious answer is nothing, or air. And the obvious answer is beside the point, because I want you to strip all of that away. Take out the air. Take out the drifting dust, the water vapor, the stray photons bouncing through, the neutrinos passing through your hand, and the wall behind it without noticing either one. Take out every field you can imagine, if such a thing is even possible. Now ask again, what is left between your finger and your thumb? Here's the strange part. You'll find you actually have two separate instincts about this, and they flatly contradict each other. The first instinct insists that something is still there. There is a gap, the gap has a size, and 10 centimeters of real physical space is sitting between your fingers right now. A piece of the same continuous material that stretches out past your bed, past your walls, past the atmosphere, past the moon, and onward across the galaxy without ever running out. On this view, space is a thing in its own right. It is the container the universe happens to be sitting inside, and it would still be there, waiting, even if the universe had never existed to fill it. The second instinct says the exact opposite. There is no stuff between your fingers at all. There is only the fact that your finger and your thumb happen to be a certain distance apart, and that fact is a relationship between two objects, not some substance quietly occupying the space in between. On this view, if you removed every object in the universe, you would not be left with an empty stage waiting patiently for new actors. You would be left with nothing at all, because there was never a stage to begin with. There were only ever the actors, and the distances between them, and distances aren't made of anything. They're just true, the way a comparison is true. Both of these instincts feel completely obvious the moment you consider them, and that's exactly the trap, because they cannot both be right. Physics has been quietly arguing about which one wins for over 3 centuries, and it still hasn't produced an answer that everybody accepts. Now try the same experiment with time, which turns out to be even harder, because time refuses to hold still long enough to be examined. Something happened a moment ago. Something is happening right now. Something is about to happen next. The picture most of us carry around without ever questioning it is a river, a current flowing steadily forward, carrying everything along with it at a fixed rate, 1 second for every second, whether or not anyone is there to notice. Empty the universe completely, and on this view, time would keep flowing anyway, silent and unmarked. A river running through a canyon with no one left to watch the water. The other picture flips this entirely. There is no river, there are only events, and those events happen in a certain order, and time is simply the name we give to that ordering. Nothing flows anywhere. Things happen, one after another, and the after is the only piece of it that's actually real. There's no current underneath carrying anything along. Here's why this matters far more than it might sound like it should. These aren't two different ways of describing the same underlying facts, the way saying half full and half empty describe the same glass. These are two entirely different claims about what fundamentally exists. And buried underneath both arguments, underneath the fight about space and the separate fight about time, there is a single idea that quietly decides the outcome of both disputes at once. That idea is not obscure. It's not some fringe concept whispered about at the edges of physics conferences. It shows up in every serious textbook on general relativity written in the last half century. It's the very first thing a working relativist reaches for when they want to understand what a particular universe is actually like on the inside. And yet it is almost never mentioned in any popular explanation of physics you have ever encountered. You can go your entire life fluently using words like space and time, the way you can drive a car for decades without knowing what happens under the hood when you turn the key. It works. Right up until the moment you actually want to know why a black hole has an edge you can never see coming. Why the beginning of the universe counts as a beginning at all, or why the most serious attempt anyone has ever made to write down a single quantum equation for the whole universe produced a piece of mathematics in which technically nothing ever happens. And when you dig into any of those answers, you find they are all written in a language nobody ever taught you. By the time tonight is over, you will know exactly what that language is. You'll know about a mathematician working almost entirely alone in England in 1914, quietly throwing away distance and duration and every measurement physics had ever relied on. keeping only a single relationship between events and rebuilding the geometry of the universe out of that alone. You'll know about a 3-page proof from 1964 that showed the entire symmetry structure of Einstein's relativity. Every strange, famous consequence of it falls directly out of that one relationship and nothing else. You'll know about a set of results from the 1970s that pushed this idea into curved space-time, into the real universe, the one with gravity and mass and galaxies in it, and showed that this single structure determines 9 out of every 10 numbers needed to describe the shape of reality at any given point. And you'll find out exactly what the missing 10th number is and where it secretly comes from. And before any of that, we have to go back to a bucket of water swinging on a twisted rope, and to a question a philosopher once asked a mathematician about shifting the entire universe 10 meters to the left, a question that sounds almost childish, and that took physics more than 200 years to actually answer. Part 2. The Bucket and the 10 meters. In July of 1687, Isaac Newton published the book that turned physics into a genuinely quantitative science. And before he wrote down a single law of motion, before any of the mathematics that would go on to predict the tides and the orbits of planets and the return of comets decades in advance, he stopped to state something else entirely. Tucked into the opening pages of the Principia, before the laws, before the proofs, he told the reader plainly what he believed space and time actually were. Absolute space, he wrote, in its own nature, without relation to anything external, remains always similar and immovable. Absolute time, of itself and from its own nature, flows equably, without relation to anything external. Read that again slowly, because it's doing something unusual. It isn't a result. Nothing earlier in the book proves it. It's a flat declaration about the basic furniture of reality, placed at the very front of the most successful physics text ever written, stated with the total confidence of a man who considered the matter already closed. Space, in his telling, is a container. It has always been there. It never moves. It does not care in the slightest what happens to be sitting inside it. Time is a current, running at exactly the same rate everywhere, a current that would keep flowing at that same rate even in a universe containing absolutely nothing at all. Newton needed this idea to make his own laws work. His laws only hold true in certain reference frames, the ones physicists call inertial, where an object left alone travels forever in a straight line at a constant speed unless something pushes it. But try to define what an inertial frame actually is without appealing to some fixed absolute space, and you find yourself running in a circle. An inertial frame is the frame in which the laws hold, and the laws hold in inertial frames. Absolute space was the thing that broke that circle. It handed Newton a fixed backdrop against which real motion could be measured, rather than leaving motion as nothing more than a matter of opinion depending on who was watching. And Newton didn't just assert this, he had an argument for it, and it's a genuinely clever one. It involves a bucket. Take a bucket of water and hang it from a rope. Twist the rope tightly, over and over, and then let it go. In the first instant, the bucket begins spinning rapidly, but the water inside hasn't caught up yet. It sits there, motionless relative to the room, while the bucket spins around it. At this moment, the bucket and the water are in fast relative motion, and the surface of the water is perfectly flat. Now wait. Friction between the bucket and the water slowly drags the water into rotation until eventually the two are spinning together at rest relative to each other. And now the surface of the water is no longer flat. It has climbed the sides of the bucket, curving into a hollow at the center. Now reach in and stop the bucket by hand. The water keeps spinning on its own. The bucket and the water are once again in rapid relative motion to each other, exactly as they were at the very start. And the surface of the water stays curved. Look closely at what that sequence actually proves. When the bucket and the water were moving relative to each other, the surface was flat. When they were at rest relative to each other, the surface was curved. The shape of the water's surface does not track the relative motion between bucket and water at all. So whatever is causing that curvature, it cannot be caused by rotation with respect to the bucket. And it can't be caused by rotation with respect to the room either, or the floor, or the walls, or the earth, or anything else nearby you might want to point to, because the water behaves exactly the same way no matter where in the universe you happen to run the experiment. Newton's conclusion was blunt. The water knows it is rotating, and the only thing left for it to be rotating with respect to is space itself. That argument held the field for 200 years, and honestly, it's still the single strongest piece of evidence the container view of space has ever produced. Rotation leaves marks on the world. Spin a bucket, or a planet, or an entire galaxy, and something physically real happens as a result. The water climbs the walls. The planet bulges at its equator. The galaxy's arms wind outward into a spiral. Uniform motion in a straight line, by contrast, you can never detect from the inside at all. That's the whole reason a smoothly moving train feels indistinguishable from a stationary one. But acceleration, and rotation in particular, seem to announce themselves from within a closed system, with the curtains drawn, without any need to look outside at all. And that looks, for all the world, exactly like a system somehow sensing its motion relative to space itself. Then, nearly 2 centuries later, an objection arrived from a man who never once held a physics chair and never ran a single experiment of his own in his life. Gottfried Wilhelm Leibniz was a lawyer by training, a diplomat by profession, a mining engineer at various points, the designer of one of the earliest mechanical calculating machines, and, not incidentally, the co-inventor of calculus, which is the actual reason he and Newton spent so much of their later lives despising each other in print. But his objection to absolute space had nothing to do with any of that rivalry. It grew out of a principle he applied to everything he examined. Nothing, Leibniz insisted, is ever the case without a sufficient reason for it being that particular way rather than some other way. Applying that principle to space, Leibniz argued that space simply is not a thing. In his own words, space is an order of coexistences, a way of describing how objects stand in relation to one another. In the same sense that a family tree describes how people are related without there being some separate physical object called the family hovering behind them in the room. Time, in the same way, is merely an order of successions, not a river carrying events along, just a sequence, one thing after another, with nothing underneath doing the carrying. And then Leibniz asked the question that has been sharpening minds for over 300 years since. Suppose you took the entire universe, every particle, every planet, every observer, every field of force and, leaving every single distance between them exactly as it currently is, you shifted the whole thing 10 meters to the left. Would anything at all be different? Newton's picture is committed to saying yes. The matter of the universe would now be sitting at genuinely different absolute positions in space. It would be a truly different state of the world, even though no observer anywhere could ever possibly detect the change, because detecting it would require some fixed marker existing outside the universe to measure against, and there isn't one, and there never could be one. Leibniz's answer is that the question itself is broken. Nothing measurable has changed. Not a single relationship between any two objects is any different. Every distance, every angle, every possible observation you could ever make comes out identical either way. There is no genuine fact about where the universe sits. Because where the universe sits was never a meaningful description of anything to begin with. If Leibniz argued writing in 1716, so he phrases it in terms of God doing the deciding, where a modern physicist would phrase it in terms of the laws of nature if there were ever a choice to be made between placing the universe here and placing it 10 meters to the left. There would be no possible reason to prefer one over the other, and so there is no choice being made at all. There aren't two different possible universes here. There is exactly one universe, described twice over. This exchange happened almost entirely in writing, and it happened fast. Between November of 1715 and November of 1716, Leibniz traded letters with Samuel Clerk, an English clergyman and philosopher who was, by any reasonable reading, acting as Newton's own mouthpiece in the dispute. 5 letters from Leibniz, 5 replies from Clerk. The go-between carrying the letters back and forth was Caroline, Princess of Wales, who had studied under Leibniz years earlier, corresponded with him regularly, and appears to have deliberately engineered the whole exchange because she wanted the argument preserved on the historical record. It stands today as one of the single most consequential philosophical debates in the entire history of science, and it never actually ended, it simply stopped. Leibniz died in November of 1716 with his 5th letter left unanswered, and Clerk published the full correspondence the following year in an elegant bilingual edition, arranging things so that he himself got the very last word in print. That is more or less how the argument was received for the following century and a half. Newton won, but mostly by default, because Newton's physics worked. Because it could place a planet exactly where you predicted it would be years in advance, and because the other man was no longer alive to keep arguing back. But nothing had genuinely been settled. Leibniz's question had not been answered so much as it had simply been outvoted by circumstance. And there remained one thing his relational picture of space could not explain at all. One thing that Newton's bucket kept sitting there quietly doing, spinning on its rope, its water climbing the walls, patiently waiting for someone to explain it properly. If space really is nothing more than the relations between objects, then what, precisely, is that water rotating with respect to? It would take 167 more years before anyone produced a serious answer to that question. And when the answer finally came, it arrived from a physicist who believed the entire question of what things actually are was, in itself, a distraction from what could actually be measured. Part 3. The argument nobody could settle, and the physicist who tried anyway. Ernst Mach published The Science of Mechanics in 1883, and it isn't really a physics textbook in the ordinary sense. It's a historical and critical dissection of how physics arrived at its own ideas, written by a man who held an unusually severe standard for what could even count as a real, meaningful statement about the world. Mach's rule was simple, and it was merciless. If a claim could not, in principle, be checked against something observable, some reading on an instrument, some sensation that a human being could actually have, then it wasn't physics. It was decoration dressed up as science. Absolute space failed that test instantly. Nobody had ever seen it. Nobody had ever measured it. Nobody had ever detected a single one of its supposed properties directly. It appeared inside Newton's system purely as a piece of invisible scaffolding, quietly doing essential work while never once showing itself. Mach found this intolerable, and he went straight after the bucket. His counter-argument is a single sentence. and it has been quoted for 140 years since because it does so much damage with so little effort. Newton, Mac pointed out, had performed an experiment using a thin metal pail holding a few litres of water, and from that modest little experiment he had drawn a sweeping conclusion about the fundamental structure of the entire universe. But nobody, Mac wrote, is in any position to say what would happen if the walls of that vessel were built up until they were several miles thick. Sit with what that objection actually does to the argument. Newton's entire inference depends on the assumption that the surrounding matter is irrelevant to what the water does, that the water's curved surface has nothing whatsoever to do with the bucket, purely because the bucket is small and light. Mac's reply is that the bucket is small, precisely, and so of course its gravitational influence is far too tiny to detect. That tells you nothing at all about whether ordinary matter is actually what the water is responding to. Build the bucket the size of a mountain range, give it the mass of an entire planet. Nobody has ever run that experiment, and until somebody does, Newton's conclusion is resting on nothing more than an untested assumption dressed up as a proof. So what then is the water actually rotating relative to? Mark's answer was elegant in its scope. Relative to everything else there is. Relative to the total distribution of matter across the whole universe, the distant stars, in the language of his era, which effectively meant the entire visible cosmos taken together. Inertia, on this view, is not some private property that a body carries around with it in isolation. It is a relationship between that body and every other piece of matter that exists. Take away the stars entirely, and rotation stops meaning anything at all, because there would be nothing left for the rotation to be measured against. A single lone bucket, floating in an otherwise completely empty universe, would have no way whatsoever to curve its own water. This is relationalism with genuine physical teeth in it. It isn't a philosopher's abstract word game about shifting things 10 meters sideways. It's a real, testable physical claim. Local inertia, Mac is saying, is set by distant matter. The reason it's difficult to push a heavy object here in your own living room has something to do, in some deep and strange way, with the mass of galaxies you will never travel to in your lifetime. Newton, interestingly, had already anticipated something very much like this reply, and he had a harder, more brutal version of the bucket experiment waiting in reserve for it. Imagine, instead of a bucket of water, two solid spheres connected by a length of cord, floating alone in a universe that contains absolutely nothing else at all. If that pair is rotating, the cord connecting them will be under tension, and crucially, you could measure that tension directly from inside the system without ever needing to look outside it or reference anything external whatsoever. So rotating with respect to what exactly? Mac's answer requires distant matter to make the concept of rotation meaningful in the first place, and in this thought experiment, by construction, there is no distant matter at all. The relationalist is left with only two uncomfortable replies. Either the tension in the cord simply wouldn't appear at all, which nobody has any way to test, or the entire thought experiment is somehow illegitimate to begin with, because a universe containing only two spheres and nothing else isn't a universe that could actually exist. Neither reply is especially satisfying, and physicists are, in various forms, still making one or the other of them today. A young patent clerk in Bern read Mac's book, and it changed him. Einstein said, more than once, and in more than one place, that Mac's critique had been genuinely decisive for him, that it was the specific book that taught him to distrust any concept that couldn't eventually be cashed out in terms of actual observations. When he set out to build general relativity years later, he fully expected the finished theory to deliver Mach's idea in rigorous mathematical form. In 1918, he gave the idea an official name, calling it Mach's principle, and for a stretch of time he genuinely believed his own field equations had captured it completely. This is where the story turns awkward, and the awkwardness is the honest part worth sitting with. General relativity is Machian in certain specific respects. It states, without any ambiguity, that matter determines the geometry of spacetime, and that the local standard for what counts as unaccelerated motion is set entirely by that geometry. Spin a sufficiently massive object, and it will drag the local definition of not rotating around with it, a real physical effect known today as frame dragging. For decades this sat purely on paper, an elegant prediction nobody had the technology to check. Then, a satellite went up specifically to check it. Gravity Probe B launched in April of 2004, carrying 4 gyroscopes that rank among the most perfectly spherical man-made objects that have ever existed, fused quartz spheres, machined round to within roughly 40 atomic layers of tolerance. Scale one of those spheres up to the size of the Earth, and its single tallest mountain would stand only a couple of meters high. The satellite locked its orientation onto a distant guide star and simply watched for a full year to see whether the spin axis of those gyroscopes drifted at all. They drifted. There were 2 separate effects buried in that drift. The larger one, called geodetic precession, comes purely from the curvature of spacetime surrounding Earth's mass, and it measured in at roughly 600 milliarc seconds of drift per year, matching Einstein's prediction to within about 0.3%. The smaller effect, the true frame-dragging signature, caused by Earth's own rotation physically dragging spacetime around with it, came in at about 37 milliarc seconds per year. That is an angle so small that if you tried to sketch it on the night sky, it would take roughly 100,000 years for it to sweep across a distance equal to the width of the full moon. It matched Einstein's prediction to within about 19%. A completely separate and much cruder confirmation came from an entirely different method, using the Leibniz satellites and later a satellite called LAIRS, nothing more than passive metal spheres studded with mirrors, launched into orbit for the sole purpose of having ground-based lasers bounced off them. By tracking the position of these spheres for years and watching their orbits very slowly twist around the Earth, researchers extracted the same frame-dragging signature using nothing but reflected laser light and sheer patience. 2 wildly different techniques, one exquisitely precise and one almost brutally simple, both found the exact same twist woven into space-time itself. That is Mach's intuition, at least partly, vindicated by a machine quietly orbiting the planet. Rotating matter genuinely does drag the local standard of rotation around with it. The distant stars really are, in some real sense, involved in what it even means to spin. But only partly, because general relativity also permits perfectly valid solutions containing no matter whatsoever that still possess a well-defined inertial structure, empty universes in which the very concept of not rotating still has a precise meaning, which is exactly the situation Mach's principle said should be impossible. The theory also permits solutions where the entire universe rotates as a whole with nothing at all outside it for that rotation to be relative to. Einstein noticed this tension, and it bothered him for the rest of his career. He gradually stopped claiming that general relativity fully implemented Mach's principle, and by the end of his life he had largely stopped bringing the principle up at all. So the argument between the container and the relations never actually got resolved. It got inherited. General relativity took Newton's fixed, rigid stage and made it flexible, capable of stretching, bending, rippling, and even carrying energy of its own. In doing so, it made the stage far more thing-like than Newton himself had ever dared to claim. Because Newton's absolute space could never do anything at all, while Einstein's space-time visibly, measurably does. And at the very same time, it made the geometry of that space-time depend directly on the matter within it, which is precisely what a relationalist had always wanted. The theory, in effect, says yes to both sides of the argument, just in different sentences within the same equations. And that is exactly where the whole question would have permanently stalled if the very same theory hadn't quietly handed physicists a completely different way of asking it altogether. Because buried inside relativity, underneath all the curvature, underneath the field equations, underneath every rippling gravitational wave ever detected, there is a structure that is neither a container in Newton's sense, nor a set of relative distances in Leibniz's sense. It is a pattern, a simple record of which events in the universe are able to reach which other events, and absolutely nothing more than that. And in 1905, when Einstein first wrote down the mathematics that would eventually lead to this structure, not even he understood that it was the important part. Part 4. The welding of space and time. Einstein's paper from June of 1905 wasn't trying to say anything at all about the fundamental nature of space. It was trying to fix an embarrassment, and the embarrassment was this. Take a magnet and take a loop of wire nearby. Move the magnet toward the loop, and a current flows through the wire. Now hold the magnet perfectly still instead, and move the loop toward the magnet instead. The exact same current flows at exactly the same strength every single time without a single exception. But the textbook explanations for these two situations at the time were completely different from one another. In the first case, physicists said a changing magnetic field creates an electric field, and that electric field is what pushes the charges through the wire. In the second case, there is no changing field anywhere at all. Instead, the charges themselves are physically moving through a perfectly static field, and they feel a magnetic force as a direct result of that motion. Two entirely different mechanisms, described by two entirely different sets of equations, producing one identical outcome every single time, with no exceptions ever observed. Einstein's opening move, in effect, was to say that this cannot possibly be a coincidence. If the actual physical outcome only ever depends on the relative motion between the magnet and the loop, and never on which one you decide is really moving, then the underlying theory itself should reflect that from the very beginning, rather than smuggling in two separate stories that happen to agree by luck. He took that sameness as the deeper truth and rebuilt the whole of mechanics around it. The consequences arrived almost immediately, and they were not gentle. If the speed of light really is the same for every single observer, regardless of how fast or in what direction that observer happens to be moving, which is exactly what the electromagnetic theory of the era demanded, and exactly what every careful experiment kept quietly confirming then, several things fall out of that single assumption whether anyone wants them to or not. Moving clocks run slow. Moving objects contract along their direction of travel. And most dangerously of all, two events that one observer judges to be happening at precisely the same moment will be judged by a second observer, moving relative to the first, to be happening at genuinely different moments entirely. That last consequence is the one that brings the whole old structure crashing down. The relativity of simultaneity does not merely say that human beings have some trouble getting their watches perfectly synchronized with one another. It says there simply is no fact of the matter about which distant events are happening right now, anywhere in the universe. Two observers, passing each other on a street, both perfectly competent, both equipped with flawless instruments, will each produce a genuinely different list of everything currently happening across the cosmos, and physics offers absolutely no way to say which list is the correct one, because there is nothing left for correctness to even mean in that context. Newton's universal river of time, flowing equably everywhere at once without relation to anything external whatsoever, was simply gone. Not slowed down, not adjusted at the margins. There is no such thing as a single universal moment shared by the entire universe. There is only ever a moment for someone in particular. It's worth pausing here because it's easy to hear this and assume it's some tiny effect confined to spaceships travelling at absurd speeds, a curiosity with no bearing on ordinary life. It isn't. The size of the disagreement about simultaneity actually grows with distance, and it grows quickly. For two events separated by a single light year of space, an observer moving at just 30 kilometers per second, relative to another which isn't a spaceship speed at all, it's simply the ordinary speed at which the Earth orbits the Sun, will place those two events roughly 100 seconds apart in time, compared to how the other observer judges them. Push the separating distance out to millions of light years, and even ordinary walking speed is enough to shift that disagreement all the way out to days. We'll return to that particular fact later, in a way you may not find entirely comfortable. The person who first saw what had actually happened in Einstein's paper wasn't Einstein at all. It was his old university mathematics teacher, a man who had not been especially impressed by him as a student. Hermann Minkowski had taught Einstein in Zurich and later described him, privately, as a lazy dog who never bothered much with mathematics at all. But when Minkowski sat down and read the 1905 paper years later, he recognized something inside it that Einstein himself had never made explicit. All of those strange, disorienting effects, the slowed clocks, the shrinking rulers, the vanishing simultaneity, weren't actually a loose collection of separate distortions happening to line up conveniently. They were shadows, all cast by a single underlying geometric structure. And if you wrote the whole thing down properly, in 4 dimensions instead of the usual 3, that structure became, in a strange way, almost simple. On the 21st of September 1908, at a meeting of German scientists and physicians held in Cologne, Minkowski stood up to deliver a lecture that has outlived nearly everything else spoken at that conference. The views of space and time he was about to present, he told the room, had sprung directly from the soil of experimental physics, and that was precisely where their real strength lay. They were, he said, genuinely radical. From this point forward, space by itself and time by itself were doomed to fade away into nothing more than shadows, and only a kind of union between the two would go on preserving any independent physical reality at all. That union isn't a piece of poetry, it's a specific, calculable quantity, and it's the entire reason that lecture ended up mattering as much as it did. Take any two events, anything at all that happens anywhere in the universe, measure how far apart they are in space, measure how far apart they are in time. Any two observers who happen to be moving relative to one another will disagree about both of those numbers individually, and crucially, neither one of them will be wrong. But now take the spatial distance between the two events, square it, and subtract from that the time between them multiplied by the speed of light, itself also squared. That particular combination, that specific subtraction, comes out identical for absolutely every single observer in the universe, no matter how fast, or in what direction they happen to be traveling. It's called the space-time interval, and it is the thing that is actually genuinely there, independent of anyone's point of view. Everything you have ever casually heard about relativity being a theory that says everything is relative gets this exactly, precisely backwards. Relativity is, at its core, a theory about what remains absolute. Individual measurements of space and individual measurements of time turn out to be nothing more than perspectives on something else entirely, the way the length of a shadow cast on the ground is only ever a perspective on the solid object actually casting it. Change your own angle relative to the light source, and the shadow's shape and length will change freely. The object itself never does, and the entire physical content of relativity turns out to be hiding inside a single character in that equation, the minus sign. If that combination had instead come out as a plus distance squared plus time squared rather than distance squared minus time squared, then time would simply be a fourth ordinary spatial direction dressed up in strange units. And space-time would collapse into nothing more than ordinary four-dimensional space wearing an unfamiliar coat. There would be no speed limit built into the universe, no causal structure worth speaking of, no meaningful distinction between past and future at all. It is that single minus sign that makes time genuinely different in kind, not merely different in name, from the three dimensions of ordinary space. And it is that same minus sign that quietly sorts the entire universe into distinct categories. That combination, the interval, can come out one of exactly three ways. It can come out negative, which happens whenever two events are separated by more time than the distance between them could ever have been crossed by light. A pair like that is called time-like separated, and something travelling slower than the speed of light really can be present at both events in turn. You, sitting right where you are this very second, and you, sitting in that same spot 1 minute from now, are time-like separated from one another. Or the interval can come out to exactly zero, which happens precisely when the separation between the two events is exactly what a beam of light would cover in that stretch of time. A flash of light leaving a distant star, and that same flash finally arriving in your eye years or centuries later, are separated by an interval of exactly nothing at all, no matter how many trillions of kilometers of empty space lie physically between them. This is called null separation. Or finally, the interval can come out positive, which happens whenever two events are farther apart in space than light could possibly bridge in the amount of time available between them. That pair is called space-like separated, and here's the crucial part: no object, no signal, no influence of any conceivable kind can ever be present at both events. Nothing travelling at any speed the universe permits connects them. Not now, not ever. That threefold sorting sounds, on the surface, like a bit of bookkeeping trivia. It is, in fact, the exact concept this entire night is going to slowly circle in on, and we've just met it here, quietly, without ever giving it its proper name. Minkowski never got the chance to develop the idea any further. Less than 4 months after that lecture in Cologne, in January of 1909, he died suddenly of a ruptured appendix. He was 44 years old. Einstein's initial reaction to Minkowski's geometric reformulation of his own theory, notably, had been dismissive. He called it superfluous learnedness at the time, and grumbled privately that now that the mathematicians had gotten their hands on relativity, he could barely recognize his own theory anymore. Within just a few years, though, his mind had completely changed, and for a very concrete reason. When Einstein tried to extend relativity to include gravity as well. He found he could not take a single meaningful step forward without leaning entirely on Minkowski's four-dimensional geometry. General relativity, in the end, is written in the mathematical language of a man who never lived to see it used. But there is something folded into that threefold sorting of events past, future, and everything forever unreachable in between that Minkowski's audience in Cologne never stopped to examine that day, and that most people who encounter relativity even now are never actually shown. The categories aren't really sorting things by distance at all, not fundamentally. They are sorting the universe by something else entirely. And once you see clearly what that something else actually is, the speed of light stops looking like a speed limit and starts looking like something considerably stranger. Part 5. What relativity actually forbids. Pick any event you like. It doesn't matter what. A candle being lit in a quiet room. A single atom inside a smoke detector releasing a particle. A word spoken aloud at one precise instant in one particular kitchen. The moment that event happens, light leaves it in every possible direction at once, spreading outward as a sphere that grows at 300,000 kilometers every second. After 1 second, that sphere has already swelled to 300,000 kilometers in radius, most of the way to the moon. After roughly 8 1/3 minutes, it has reached and swallowed the sun. After a little over 4 years, it has reached the nearest neighboring star. It never slows down, and it never stops growing. Now sketch that on paper, with space running sideways across the page and time running upward. That expanding sphere of light becomes a cone opening upward into the future. And because the same physics runs equally well backward, light was also arriving at that original event from every direction just before it happened, which gives you a matching cone opening downward into the past. 2 cones joined at a single point, the event itself, one stretching above it, one stretching below. This is what's known as the light cone, and it's almost always introduced as nothing more than a picture of where light happens to travel. That's actually the smaller half of what it really is. The cone is, above all else, the boundary of influence. Any event lying inside the future half of that cone can, in principle, be reached by something travelling slower than light, a particle, a signal, a hand reaching out, an entire chain of 10,000 intermediate physical causes strung together, which means the original event genuinely can be a cause of it. Any event lying outside that cone, by contrast, cannot be reached by anything at all, not by a slow process, not by a fast one. There is no sequence of physical events, however clever, however roundabout, that begins at the first event and manages to arrive at the second. They are sealed off from one another, permanently and completely, and no future technology and no future scientific discovery will ever change that, because the sealing isn't a limitation of engineering, it's a limitation of what causation itself is even allowed to be. This is what relativity actually forbids. Not motion faster than light. Exactly, that's the version taught in classrooms, because it's easier to say. What relativity truly forbids is influence travelling outside the cone. The cone is a statement about causation, full stop, and the speed of light is simply the number that happens to set its slope. And here is the part that makes the entire structure click into place. The single most quietly astonishing fact buried inside special relativity. Take 2 events that sit inside each other's cones, time-like separated, genuinely capable of influencing one another. Every observer in the entire universe, no matter how they happen to be moving, will agree completely on which of the 2 events came first. The order between them is absolute. There is no reference frame, no speed, no clever trick of motion that could ever reverse it. If the candle was lit before the room grew bright, then in every possible description, given by every possible observer anywhere, the candle was lit before the room grew bright. Full stop, no exceptions. Now take two events that sit outside each other's cones, space-like separated, incapable of ever influencing one another in either direction. Here, observers genuinely and flatly disagree about the order, and no one's answer is privileged over anyone else's. One observer insists event A happened first. Another insists event B happened first. A third insists they happened at exactly the same moment. All three of them are correct simultaneously, and the underlying question of which one truly happened first turns out to have no actual content to it whatsoever. Set those two facts side by side and look closely at the scene running between them. Relativity scrambles the order of events completely, and it only ever does this in the specific cases where no causal relationship between them was ever possible in the first place. It preserves the order absolutely, with zero exceptions, in exactly the cases where one event genuinely might have caused the other. The disagreement between observers is confined, with perfect surgical precision, to only the pairs of events where that disagreement could never actually matter to anything. That isn't a coincidence, and it isn't a convenient patch bolted on afterward. It's what the entire theory is actually made of, underneath everything else. Relativity will never, under any circumstance, allow two observers to disagree about whether a cause came before its own effect. It will only ever let them disagree about pairs of events where causation was never remotely on the table to begin with. The relativity of simultaneity, which sounds on its face like the theory casually throwing away objective truth, turns out on closer inspection to be the theory carefully protecting objective causation, while discarding only the one part of truth that never carried any causal weight in the first place. This also quietly explains something that most people are taught as two entirely separate, unrelated rules. Travelling faster than light and travelling backward in time are not two different impossibilities that just happen to sit next to each other in a textbook by coincidence. They are the exact same impossibility, simply described from two different vantage points. A signal that manages to outrun light, according to one observer's account of events, will arrive before it was ever sent, according to a second observer's equally valid account. And both accounts are entirely correct at once. So the very moment you allow anything at all to travel outside the cone, you have quietly allowed effects to precede their own causes, and the absolute ordering that had been protecting causation the whole time collapses instantly. The cone was never a wall built to hem travellers in. It's the precise shape of the guarantee that events happen in a genuine, meaningful order. And space-like separation, it's worth saying clearly, is not some exotic condition reserved for distant galaxies. Two events happening just 1 meter apart and less than about 3 billionths of a second apart in time are already sitting outside each other's cones. This is exactly why the timing electronics used in certain delicate quantum experiments are engineered with such obsessive, almost paranoid precision. To prove definitively that two separate measurements could not possibly have communicated with one another in any way, experimenters have to arrange for those two measurement events to be space-like separated, which at ordinary laboratory distances means winning an outright race against light itself, with margins measured in mere nanoseconds. Once you've truly seen this, the speed of light stops looking like a fact about light at all. Light happens to travel at that particular speed because light is massless, and anything massless in this universe is obligated to travel at exactly that speed, no faster and no slower. But the speed limit itself comes first. It is the conversion factor between space and time, the single number that decides in advance which pairs of events in the entire universe are even capable of being causally connected, the fixed slope of every cone everywhere. Turn off every single light source in the universe at once, and this underlying structure would remain exactly, precisely where it was. A more honest name for it, one that a number of physicists now use quite deliberately, is the speed of causality. You can confirm that this really is a structural limit rather than merely a fact peculiar to photons, because other things obey the exact same cone. On the 17th of August 2017, the gravitational wave detectors sitting in Louisiana and in Washington, along with a third detector in Italy, registered the final violent spiral of two neutron stars colliding and merging into one. Gravitational waves are not light. They are not built from photons. They are not electromagnetic radiation in any sense. They are not produced by the same underlying mechanism as light. And they are not detected using the same physics as light either. They are ripples in the actual geometry of spacetime. And this particular ripple was detected by measuring a 4-kilometer long detector arm changing length by a fraction smaller than the width of a single proton. 1 3/4 seconds after that gravitational signal arrived, a burst of gamma rays arrived from that exact same patch of sky. The merger itself had taken place roughly 130 million light years away. Sit with those two numbers side by side for a second. 130 million years of travel through space. Just 1 3/4 seconds of difference upon arrival here on Earth. And that tiny remaining gap is most plausibly explained by the extra time it simply took the gamma rays to fight their way clear of the surrounding stellar wreckage, rather than by any genuine difference in travel speed between the two signals. That single measurement pins down the difference between the speed of gravity and the speed of light to within a few parts in 1,000 million. Gravity and light share absolutely no underlying mechanism whatsoever. What they do share, and the only thing they share, is the cone. Two completely unrelated phenomena obeying precisely the same limit, purely because the limit was never really about either one of them individually to begin with. There's one more thing worth saying about cones before we go looking for the person who first genuinely understood what they were, and it's the personal, intimate version of all this. You have a past light cone of your own, right now, tonight. Everything you have ever seen, everything you have ever heard, every single particle that has ever physically touched you in any way, at any point in your life. Every event that has ever affected you in any manner whatsoever lies somewhere on it or safely inside it. It isn't a region of space at all. It's a region of history, and it narrows down to a single sharp point at the exact moment your own existence began. Everything sitting outside that cone has never once been able to reach you, and never will have been able to. And you also have a future light cone stretching ahead of you right now, the complete set of every event you could still, even in principle, ever go on to affect. It opens outward ahead of you and keeps widening forever, and everything lying outside it is beyond your reach in the most absolute sense the universe has to offer. Not merely far away, genuinely, permanently disconnected from you. Every single human being alive tonight is, in effect, a small pair of cones drifting slowly through a vast structure of relationships that has already decided in advance exactly what could ever possibly come to matter to them. For nearly 50 years after Minkowski first sketched those cones on a chalkboard, almost everyone in physics treated them as a downstream consequence, something you could derive, sure. But only once you already had the full geometry of space-time in hand the distances, the durations, the complete metric worked out first. One man, working almost entirely by himself in Cambridge, decided to try it the other way around entirely. Part 6. The geometry hiding inside the word after. Alfred Arthur Robb was born in Belfast, studied at Cambridge, spent a period of time working in Gittingen, and then returned to Cambridge, where he worked mostly alone for the remainder of his career. He is not a famous man. He rarely appears in the popular histories of physics. He never held a major chair at any university. He founded no school of thought, and he had almost no students to speak of. What he did have was a question that nobody else around him had thought to seriously ask. In 1912, everyone in the field was busy working out the countless downstream consequences of relativity. Robb wanted to know, instead, what relativity was actually made of underneath. And in 1914, he published a book with Cambridge University Press titled A Theory of Time and Space, in which he attempted something that still reads, even now, as more than slightly reckless. He threw away distance entirely. He threw away duration. He threw away clocks, rulers, coordinates, simultaneity, velocity, and the metric itself. He kept exactly one single thing, a relation between events, which he expressed using the plain word after. That is the entirety of his vocabulary. Given any two events, either the second one is after the first or it is not. After, in strictly physical terms, means capable of being influenced by sitting inside the future cone of the other. There are no numbers involved anywhere in this. There is no notion of how much later, or how far away, or in which particular direction. There is only a bare pattern of which events lie in the future, of which other events the exact same list you would arrive at if you went through every single pair of events in the entire universe and made one simple mark next to each pair. Yes or no. From that alone, and a short handful of accompanying postulates about how the relation is required to behave, Robb reconstructed the whole of Minkowski's geometry from scratch. The light cones, the number of dimensions spacetime actually has, the distinction between time-like and space-like separation, the Lorentz transformations that govern how clocks and rulers change between observers, the interval itself, all of it derived entirely from a structure that contains no measurements whatsoever. The book is written in a style so austere and axiomatic that it was more often admired from a distance than it was actually read closely. Robb worked in near total isolation, drew his own diagrams of what he called the conical order light cones, essentially, decades before they became standard furniture in every physics classroom, and stated plainly in his preface the conclusion he believed he had proven, that the relation of before and after is the truly fundamental one, and that time, in some deep sense, is actually more basic than space itself. And then the field simply moved on without him. For roughly half a century, his results sat quietly in the scientific literature, cited by almost nobody at all. He had, in fact, been building toward this conclusion for years already. An earlier book of his, Optical Geometry of Motion, had appeared back in 1911, and it already contained the same core instinct that would come to define his entire body of work, that the physics of light is not, at bottom, really about light at all, but about the order in which events are permitted to be seen happening relative to one another. His 1914 book pushed that instinct as far as it could possibly go, and then rather further than the readership of his time was actually willing to follow him. Let me try to make what Robb actually accomplished feel genuinely vivid, because stated abstractly. It's easy to nod along politely without truly registering the size of what he pulled off. Imagine someone hands you a ledger. It is unimaginably enormous, one single line for every single pair of events that has ever occurred anywhere in the entire universe, and every one of those lines contains exactly one mark. Yes, if the first event could possibly have reached the second. No, if it could not have. That is genuinely all the ledger contains. There are no distances written anywhere in it, no dates, no durations, no coordinates of any kind, no clock readings, nothing you would ordinarily be willing to call a measurement. You open this ledger somewhere near the middle and start working through it. You notice that certain events form long, unbroken chains, each one reachable from the last in an unbroken sequence, and you slowly realize you are looking at the entire history of a single object, a stone, a star, a person's life. You notice that some of these chains are densely packed with connections to their neighbors, while others are sparse and thin. And the overall pattern of connection quietly begins to resemble something you might call proximity, without the ledger ever once using that word. You notice regions where the pattern of yeses and nos subtly twists, where the structure of what can reach what leans systematically off to one side, and you find, without being told, that you are reading curvature, a mass sitting somewhere nearby, a gravitational field, an orbit slowly bending through the ledger's entries. You keep working through it. Eventually you find a region from which almost nothing at all manages to get out, where every single chain leads only inward and none of them ever lead back out again, and you have found a black hole, entirely on your own, without anyone ever having told you black holes even exist. You can, in principle, build the entire universe out of nothing but this one ledger, the shape of every galaxy, every orbit, every wave, every horizon, every gravitational collapse. And then, having built all of that, you sit back and realize precisely what you still cannot do. You cannot say how big any of it actually is. Not the black hole. Not the galaxy. Not even the room you're sitting in right now. The ledger will hand you the shape of absolutely everything and the size of absolutely nothing. Hold on to that fact, because it becomes the entire story later tonight. 50 years after Rob's book quietly appeared and was quietly forgotten, in 1964, a British mathematician named Christopher Zeeman published a paper in the Journal of Mathematical Physics that runs to about 3 pages in length. It's titled Causality Implies the Lorentz Group, and the title itself is essentially the whole summary of the result. Zeeman asked a question that sounds highly technical on the surface and turns out not to be. Suppose you have nothing more than the causal ordering of space-time in front of you, just the yeses and the nos, just the bare pattern of what is able to influence what. Now ask a very specific question. Which transformations, applied to that structure, leave the entire pattern exactly as it was before? What, in other words, are you actually permitted to do to space-time without changing a single yes into a no, or a single no into a yes, anywhere in the ledger? The answer Zeeman proved is that there is almost nothing you're allowed to do. You can rotate the whole structure, you can translate it, shifting everything uniformly over in some direction. You can perform what's called a Lorentz transformation, which is precisely what happens physically when you switch to describing things from the point of view of an observer moving at a different constant speed. And you can rescale the entire structure uniformly, making everything in it uniformly larger or uniformly smaller all at once. That is the complete list in its entirety. Nothing else, no other transformation of any kind, manages to preserve the causal order. Look closely at what that result actually means. The symmetry group of special relativity, the entire mathematical machinery behind every boost, every rotation, everything responsible for generating time dilation, length contraction, the relativity of simultaneity, the fixed speed limit, built into the universe. Quite literally, every strange and famous result the theory is known for turns out to be precisely, the group of transformations that leaves the causal order completely undisturbed. It isn't some additional piece of structure that had to be separately discovered and then layered on top of causality afterward. It is what causality itself looks like, the moment you go to the trouble of writing it down using coordinates. It's worth saying plainly that the actual mathematical proof here is not especially difficult. It's short, and a sufficiently determined undergraduate could work through it in an afternoon. What was genuinely difficult was believing the underlying question was even worth asking in the first place, that anyone would think to strip relativity all the way down to its bare causal ordering and simply go check what, if anything, remained. Zeeman himself spent the majority of his career working in an entirely different branch of mathematics called topology, and is arguably better known today for work outside relativity altogether. This particular paper was a short excursion into someone else's subject that ended up quietly relocating that subject's own foundations. Notice too the one single piece of freedom left standing on Zeeman's short list, because it turns out to be the loose thread running through this entire night's story. You are allowed to rescale the whole structure. You can make everything in it uniformly larger or uniformly smaller, and the causal order genuinely does not notice the difference at all. Whatever the causal ordering happens to know about the universe, it does not and cannot know how big any of it actually is. Zeeman himself was careful and generous about credit in his paper, noting that the essential core of the result had already been obtained more than a decade earlier by a Russian mathematician named Alexandrov, whose work had gone almost entirely unnoticed in the West at the time. Alexandrov had also shown something further along the way, something equally striking, that you can build the entire topology of spacetime, the full notion of which regions count as near which other regions, what a neighborhood even means, what continuity itself means, out of nothing but causal diamonds. Take every event lying after some event A and before some event B, and use those overlapping double cone-shaped regions as your basic building blocks, and the entire topology of the universe assembles itself, quietly and automatically, out of nothing but pure ordering. So by the middle of the 1960s, two separate results were sitting in the scientific literature, both largely overlooked, both quietly saying the exact same thing from two very different directions. Rob had shown you can build the full geometry of flat space-time out of nothing but the word after. Zeeman and Alexandrov had shown that the symmetries and the topology of relativity are precisely the symmetries and topology of the causal order, and absolutely nothing more than that. Both of those results, though, applied strictly to flat space-time, the idealized case, with no gravity present at all. The real universe, of course, is curved. Matter bends it, and that bending is the entire subject matter of general relativity. The obvious next question is whether any of this survives at all once you actually switch gravity on. It would take another decade to find out, and when the answer finally arrived, it turned out to be far more extreme than anyone had any real reason to expect. Part 7. 9 parts out of 10. To describe the geometry of a curved space-time completely, you need exactly 10 numbers at every single point in it. That isn't an arbitrary figure someone picked for convenience. It falls directly out of the mathematics of 4 dimensions. A symmetric object carrying 2 indices in 4 dimensions has precisely 10 independent components, and those 10 numbers, specified at every point throughout the universe, tell you literally everything there is to know about the shape of reality there, how far apart things are, how much time elapses along any given path, what angles look like when you measure them, how curvature bends orbits, delays signals, and stretches falling bodies apart. 10 numbers per point, and there is nothing further left to say about the shape of reality beyond that. This object is called the metric, and general relativity is, at its heart, simply a set of equations describing how the metric behaves. In 1976, Stephen Hawking, Anthony King, and Patrick McCarthy published a paper proposing a way to build the topology of curved space-time directly out of its causal structure alone. The result buried inside it is the one that matters most here. If you have two different spacetimes, and there exists some mapping between them that preserves the causal order which events precede which and preserves nothing else whatsoever, then those two spacetimes turn out to be related by what's called a smooth conformal transformation. The following year, in 1977, a physicist named David Malamant sharpened the result even further, showing that you actually need even less information than that. Simply knowing the class of continuous time-like curves the possible histories of ordinary objects capable of moving through space turns out to be enough, all on its own, to fix the topology of space-time, and with it the full conformal structure as well. It's worth pausing on just how ordinary Malamant's raw ingredient actually is. A continuous time-like curve is nothing more exotic than the history of something that can move. A spacecraft. A grain of dust drifting through a room. A person walking to the kitchen for a glass of water. His result says that the complete set of possible histories belonging to ordinary moving objects is all by itself enough to reconstruct the entire structure of the universe those objects happen to be moving through. You don't need the geometry first in order to get the histories. Remarkably, you're allowed to go the other way entirely. None of this was some passing side interest for Hawking. He and George Ellis had already spent the preceding decade rebuilding large stretches of general relativity on purely global causal foundations, and their landmark 1973 book on the large-scale structure of space-time is, in essence, a full textbook of causal reasoning, with long stretches that never once mention a coordinate system at all. So what exactly does conformal mean here, and how much of that full set of 10 numbers does it actually get you? It gets you 9. The causal structure, that bare ledger of yeses and nos we described earlier, determines 9 of the 10 numbers at every single point in the universe. Every fact about shape, every angle, which directions count as time-like and which count as space-like, the complete pattern of curvature, where every horizon sits, where every singularity sits, how the light cones tip and lean around a rotating mass. 9 out of 10 recovered from causality alone. The 10th is the overall scale at each point, and the reason it manages to slip through the net is easy to see once someone points it out to you. Take the metric at any given point and multiply the entire thing by some positive number. Every distance and every duration in that immediate neighborhood changes together in exactly the same proportion all at once. But the light cones themselves don't move even slightly, because a cone is defined purely by the ratio of space to time. And multiplying both space and time by the same factor leaves that ratio completely untouched. The ledger doesn't change. Not a single yes flips into a no anywhere. Angles survive the transformation perfectly intact. Sizes do not. The shape of everything and the size of nothing. There's a clean physical way to state exactly what that missing 10th number actually is. It's a volume element, a measure of how much space-time volume any given region actually contains. Hand someone the causal order and hand them the volumes on top of that, and the full metric is uniquely and completely determined. There is no third ingredient hiding anywhere. There is nothing else left to know about the geometry of the universe. This is precisely why relativists draw the particular diagrams they draw. When a physicist wants to show you the complete structure of a black hole or of an infinite expanding universe, they'll sketch a small diagram on a single page with every light ray drawn running at a neat 45 degrees, and they will happily squash an infinite space-time down into a small finite triangle in order to do it. Those diagrams work precisely because throwing away scale throws away nothing that matters causally. You can still read directly off the page what can reach what, whether a singularity sits in your future or off to one side, whether a horizon exists at all, whether some distant region could ever, even in principle, be seen. The distances are gone from the picture, deliberately, and none of the physics that actually matters goes missing along with them. Light itself, notably, cannot tell any difference at all. Massless particles travel along paths that depend only on the conformal structure. Light does not know how big the universe is. It only ever knows its shape. There's a piece of history that makes all of this feel concrete, and it happens to involve the single most expensive intellectual mistake Einstein ever made. Between 1913 and late 1915, Einstein spent 2 years talking himself entirely out of general relativity. Working alongside his friend Marcel Grossmann on an early draft of the theory, he constructed an argument he came to call the whole argument. Take a region of space-time with no matter in it at all, a whole. If your field equations are generally covariant, meaning they hold true in absolutely any coordinate system whatsoever, then you can smoothly shuffle the points inside that hole around and end up with a second solution that is different in appearance and yet fully identical to the first everywhere outside the hole. Specify the entire universe outside the hole in complete detail, and the theory still refuses to tell you exactly what the field is doing at any particular point inside it. To Einstein, at the time, this looked like a total, catastrophic collapse of determinism itself, and he drew the conclusion that generally covariant field equations simply had to be impossible. He then spent roughly 2 years constructing a deliberately weaker theory around that conclusion, a theory which, among its other flaws, gave the wrong answer entirely for the orbit of Mercury, a discrepancy he was fully aware of the whole time and simply had to live with. In November of 1915, he finally abandoned the objection altogether and wrote down the equations that carry his name to this day. The resolution is the entire reason this story matters. The two apparently different solutions inside the hole are not actually two different physical situations at all. They are one single physical situation, described twice over, because the points of space-time themselves carry no independent identity apart from the fields defined on them. There is no such thing as the point where the field would have been, existing independently of the field itself. Shuffling the points around inside the hole is, at bottom, the exact same operation as moving the entire universe 10 meters to the left. Einstein had reproduced Leibniz's own mistake 200 years later inside his own equations with his own hands, and he had to accept Leibniz's original answer before he could finally write down the correct theory. Modern relativists tend to state the resulting moral without much ceremony at all. Space-time points are not entities that carry their own identity. Only relations between things are physically real. Let's pause here and stack everything up because we're now roughly halfway through and the ground beneath us has been steadily shifting the entire time. We began with a bucket and a philosopher's question about moving the universe 10 meters sideways. Newton said space is a container. Leibniz said space is nothing more than a set of relations. The argument ran on for 2 full centuries with no way to settle it either way. Then relativity arrived, and it quietly removed the universal present, leaving only the interval behind in its place. And that interval sorts every single pair of events in the entire universe into 3 distinct categories, based purely on whether influence between them is even possible at all. That sorting is the light cone, and the cone turns out to be a statement about causation, not about light. Rob showed you could rebuild the entire geometry of flat spacetime out of ordering alone. Zeeman showed that the symmetries of relativity are exactly the transformations that preserve that same ordering. And then Hawking, King, McCarthy, and Malamud showed that in curved spacetime. In the actual real universe, with gravity fully switched on, the causal order alone determines 9 of the 10 numbers that describe the complete shape of reality, which leaves exactly 1 number left unaccounted for. 1 number per point in the entire universe, the size of things, missing from an otherwise remarkably complete account of everything. You would reasonably expect that gap to be a serious problem. In 1987, a group of 4 physicists proposed something rather different, that the missing 10th number is in fact the single biggest clue we have ever been handed about what space-time is actually made of underneath, and that supplying it seems to require the universe at its very smallest scale to not be smooth at all. Part 8. Order plus number. If causality alone gives you 9 out of 10 pieces of geometry and the missing 10th piece is simply a volume, then there's an obvious thing worth trying next. Build an entire theory out of exactly those 2 ingredients and nothing else whatsoever. That is precisely what Luca Bombelli, Johann Lee, David Meyer, and Raphael Sorkin proposed in a paper published in Physical Review Letters in 1987, titled Spacetime as a Causal Set. It stands as one of the shortest and most severe proposals in all of modern physics, and Sorkin's own summary of the entire program runs to just 4 words. Order plus number equals geometry. Here is the whole framework, stated plainly. The fundamental thing isn't a smooth manifold, it isn't a field, it isn't a string, it isn't a wave function. It's a set of discrete elements, call them events, or if you like, atoms of space-time, with a single relation defined between them, which we can call precedes. That relation has to obey exactly 3 conditions. First, it's transitive. If A precedes B and B precedes C, then A necessarily precedes C as well. This is simply the statement that chains of influence link together properly. Second, it's acyclic. Nothing is ever allowed to precede itself. There are no loops permitted, no journeys that curl back around to their own beginning. Causation only ever goes one way. And third, this is where the whole framework does something no purely continuous theory can manage. It's locally finite. Between any 2 elements in the set, there are only ever finitely many other elements sitting in between. Not an infinitely dense crowd, a countable, finite number. That third condition is the entire trick, and it's doing precisely the job that no continuum theory has ever been able to do on its own. Think back to why the smooth continuum needed a volume element bolted onto it as a separate ingredient in the first place. In an ordinary smooth space-time, any region at all, however small you shrink it, still contains infinitely many points. You cannot measure the size of a region simply by counting what's inside it, because the answer always comes out the same, regardless infinity. So volume has to be brought in separately, imported as extra structure layered on top of the causal order. In a causal set, the situation flips entirely. Ask how big a given region actually is, and you simply count the elements sitting inside it. The number itself is the volume. The missing 10th piece of the metric isn't some additional ingredient that has to be imported from somewhere else at all. It's exactly what discreteness hands you automatically, for free. Causality supplies the shape. Counting supplies the size. Nothing else is needed, and nothing else is permitted into the theory at all. The natural scale for that counting turns out to be the Planck scale. A Planck length works out to roughly 1.6 times 10 to the minus 35th of a meter. A Planck time comes out to roughly 5.4 times 10 to the minus 44th of a second. Multiply the cube of one of these by the other, and you get a four-dimensional volume of space-time so small that the resulting numbers barely mean anything human intuition can grasp. It's to a single proton roughly what a proton is to the entire solar system, and then quite a bit smaller again on top of that. At a density of roughly one element per Planck 4 volume, the entire history of the observable universe, everything, everywhere, from its beginning right up to this very moment, works out to a set containing something on the order of 10 to the 240th power elements. A 1 followed by 240 zeros. That is the total number of atoms of history in the entire visible world. So how exactly does a structure like this relate back to the smooth spacetime we actually experience every day? Through a procedure called sprinkling, and the fine details of it produce one of the most genuinely peculiar requirements found anywhere in physics. You take a region of ordinary, smooth spacetime, you scatter points into it at random genuinely, truly at random, through a process where the expected number of points landing in any given region is directly proportional to that region's volume, with absolutely no coordination happening between the points at all. You then let each pair of scattered points inherit whatever causal relationship they already had in the original smooth spacetime, and finally you simply throw the smooth spacetime itself away. What remains behind is a causal set, and if the density of points is high enough, that causal set turns out to contain essentially all of the information the original smooth spacetime ever had. The obvious question at this point is why any of this needs to be random at all. Wouldn't a neat, orderly grid be so much easier to work with? The answer is a theorem, and it's genuinely beautiful. A regular lattice simply cannot be made compatible with relativity. Lay out a grid of points evenly spaced, sitting at rest relative to some particular frame, and then boost your point of view looking at the same grid from a frame moving quickly relative to the first. The grid no longer looks the same at all. Distances measured along the direction of motion contract. So the spacing between points changes, and the resulting pattern is a genuinely different lattice than the one you started with, which means the original grid was secretly picking out a preferred frame all along specifically, the one frame in which it happens to look perfectly regular. And relativity's entire content, at its core, is the insistence that no such preferred frame exists anywhere in nature. A random sprinkling behaves in a completely different way because its points are scattered by a process carrying no correlations whatsoever. Boosting the whole arrangement produces something that is statistically identical to what you started with a different specific scatter of points, but one drawn from exactly the same underlying distribution, with absolutely no way to tell afterward which frame it was originally generated in. Bombelli, together with Joe Henson and Sorkin, proved this formally in a 2009 paper whose title states the whole moral plainly, discreteness without symmetry breaking. Sit with what that actually requires for a moment. If reality really is granular at its very smallest scale, then the individual grains absolutely cannot be arranged in any orderly way whatsoever. Not a lattice, not a crystal, not a honeycomb, not any structure carrying regular spacing at all, because every single one of those arrangements would quietly pick out a preferred frame, and in doing so, violate the deepest symmetry we have ever managed to test in physics. The fundamental structure of the world, if it truly is discrete, has to be irregular, scattered like static, random at the level where randomness stops being a description of our own ignorance and instead becomes a strict requirement of basic consistency. And the room you're lying in right now, which feels entirely seamless to you, the smooth air, the continuous surfaces, the unbroken stretch of space between your hand and the nearest wall, would, on this picture, simply be the statistical appearance of something carrying no order to it whatsoever underneath. Smoothness as an average, in much the same way that the grey tone of a printed photograph is really just an average of countless scattered black dots, with no actual grey pigment anywhere in the picture at all. The program has one genuine claim to fame, and notably, it isn't a retrodiction dressed up after the fact. It's a real prediction that arrived before the observation confirmed it. In that same period, Sorkin ran the following piece of reasoning. If space-time volume really is a count of discrete elements, then that count has to fluctuate, because counting processes always fluctuate by nature. Scatter some random number of things, and the total wobbles by roughly the square root of itself. Now, in general relativity, there exists a quantity that is conjugate to space-time volume, known as the cosmological constant, the energy of empty space itself. If volume fluctuates, then that constant should fluctuate too, and as a direct consequence, it cannot sit at exactly zero. It should instead carry a small residual value, on the order of 1 over the square root of the total number of elements involved. Run that arithmetic through for our actual universe, and you land on a number around 10 to the minus 120th power. In natural units, small, but very much not zero, and strikingly close in scale to the mysterious energy that was discovered in 1998 to be accelerating the expansion of the entire universe, the very discovery that went on to win the Nobel Prize in 2011, and that nobody has ever managed to fully explain since. Sorkin's prediction preceded that observation by roughly a decade, and it was arrived at for purely structural reasons, not by quietly fitting anything to existing data after the fact. There are honest caveats worth stating plainly. The argument only ever gives an order of magnitude rather than a precise predicted value, and building a full, working dynamics out of it remains a genuinely open problem to this day. But if the reasoning is right, then the underlying reason the universe is being pulled apart at accelerating speed is that the universe itself is fundamentally unable to count itself exactly. This is not by any means a finished theory. It carries serious unresolved problems of its own, the sharpest of which involves a strange form of non-locality. In a random sprinkling, an element's nearest neighbours, in the properly relativistic sense, end up smeared out all along its entire light cone, and there turn out to be enormous numbers of them, which makes recovering ordinary local physics unexpectedly difficult. But it demonstrates, clearly and concretely, the very point this whole night has been slowly building toward. You can take an entire universe, delete its space, delete its time, and keep only a bare list of what is able to influence what. Add nothing more than the ability to count, and you get the world handed back to you. Which raises a question nobody in 1987 was even asking yet, because it had already been answered 2 decades earlier by a man who worked out what a black hole actually is by thinking purely about causal relations, and who reportedly stumbled onto the crucial idea while simply crossing a street. Part 9. The Street Crossing. In the early 1960s, most physicists did not actually believe in black holes. The mathematics permitted them, certainly. Karl Schwarzschild had found the relevant solution back in 1916 within months of general relativity's own publication. And that solution contained a place where the equations broke down entirely and the density ran off to infinity. But everyone understood exactly how that particular solution had been obtained by assuming a perfectly spherical collapse, a perfectly round star falling inward with every last piece of matter converging exactly toward the center. Real stars aren't like that at all. Real stars spin. They carry lumps and irregularities. Their interiors are turbulent, their magnetic fields tangled and messy, and their collapse, when it comes, is chaotic. The reasonable expectation, shared by most of the field, was that in any realistic collapse, infalling matter would simply miss the exact center, swirl past it, and rebound outward again, producing something extraordinarily dense and violent, certainly, but never an actual mathematical infinity. The most influential version of this skepticism came from the Soviet physicists Yevgeny Lifshitz and Isaac Kalatnikov, who published an analysis in 1963 concluding that singularities were nothing more than artifacts of unrealistic symmetry and simply would not occur in nature at all. Roger Penrose thought the entire question could be settled without ever solving the full, brutal equations of stellar collapse, without knowing a single thing about the star's exact composition, its rotation, its magnetic field, or its precise shape. He believed it could be settled purely by reasoning about causal structure alone. In the autumn of 1964, Penrose was walking through London with a visiting colleague, the physicist Ivor Robinson. The two of them had been talking without any real pause for quite some time. Robinson was an unusually engaging conversationalist, and the discussion had carried on continuously the entire way down the street. They come to a side road. Traffic is approaching. The conversation breaks off mid-thought, because crossing a busy London street properly requires a certain amount of undivided attention. They step off the curb, cross together, and step back up onto the far pavement. Robinson resumes talking almost immediately, and the conversation simply closes back over the gap, with neither man consciously registering that a gap had even occurred. Sometime later that same day, after Robinson has already gone on his way, Penrose notices that he feels unaccountably good. Not pleased about anything in particular that he can immediately point to, just a low, quiet, unfocused elation of the kind that usually does have some identifiable cause behind it. Being a careful and methodical person, he goes looking for that cause. He works backward through the entire day, hour by hour, checking each thing that happened against the lingering feeling, and finds nothing that quite fits, until he arrives back at the moment in the middle of the afternoon when the conversation had briefly paused for that side street. And there, in those 10 silent seconds of simply crossing a road, an idea had clearly arrived, and the conversation resuming immediately afterward had quietly buried it before he'd ever had the chance to properly examine it. He digs the idea back out. It's the notion of a trapped surface. Here is what he recovered. Take any closed two-dimensional surface, imagine a sphere drawn around a collapsing star, and picture a flash of light being emitted simultaneously from every single point on that surface at once. Normally, two things happen next. the light emitted outward expands. So the outgoing wavefront ends up covering a larger and larger total area as time goes on. The light emitted inward converges instead, and its enclosed area shrinks steadily. Outward grows, inward shrinks. That's simply how surfaces behave in ordinary everyday space. A trapped surface is something else entirely, a surface where both directions of light shrink. The surrounding geometry has become so extremely curved that even the light emitted straight outward, travelling at full speed away from the surface, ends up enclosing a smaller total area a moment later than it did at the instant it was first emitted. Nothing about the particular shape of the surface matters here at all. Nothing about symmetry, rotation, lumpiness, or the exact composition of the collapsing material matters in the slightest. Once the light cones have tipped inward that far, every single future directed path available, every possible route anything at all could ever take, leads inward with no exceptions. Penrose's paper appeared in Physical Review Letters in January of 1965. It runs to just 3 pages, relying entirely on causal and topological arguments, with no symmetry assumptions whatsoever and no detailed equations of stellar structure required. It establishes that once a trapped surface has formed, and given some genuinely reasonable conditions on energy and on the broader causal structure of spacetime, the spacetime itself must be geodesically incomplete. That particular phrase is the technical, precise definition of a singularity, and it's worth stating carefully because it isn't at all what most people instinctively picture. It doesn't mean there's a single point of infinite density sitting somewhere out there. It means, instead, that there exists a path through spacetime, the potential history of some object that simply comes to an end. Follow that path forward, and after some finite amount of elapsed time along it, there is quite literally no more space-time left for it to continue into. A history simply stops, and physics has nothing further to say about what happens next, because there is no next for it to describe. Lifshitz and Kalatnikov, to their considerable and lasting credit, examined Penrose's argument carefully and publicly accepted it, revising their earlier published position accordingly. That's an unusually clean and honest way for a genuine theoretical dispute to end. Hawking, at the time, still a graduate student, picked up the very same machinery within the following year and ran it backward in time instead, applying it to the entire universe as a whole rather than to a single collapsing star. The joint Hawking-Penrose theorem of 1970 extended the result even further still. Penrose ultimately received the Nobel Prize in 2020, more than half a century after his original insight, specifically for the discovery that black hole formation is a genuinely robust and inescapable prediction of general relativity. The thing worth noticing here is exactly what the proof relied on. Not a single equation describing the star itself, only the raw structure of what can influence what. And the resulting definition of a black hole that fell out of this work is a good deal stranger than the popular picture most people carry around. The event horizon isn't a surface made of anything physical at all. It isn't a place where the equations suddenly start doing something special or dramatic. It's defined, precisely, as the boundary of the region from which no future directed path ever manages to reach infinity. That definition refers to the entire remaining future of the universe. It is not local in any sense, and it cannot ever be made local, which means there is no measurement whatsoever you could perform right at the horizon that would tell you, definitively, that you had actually arrived there. Imagine falling toward M87, the supermassive black hole sitting at the center of a galaxy 55 million light-years away, the one imaged directly by a global network of radio telescopes back in April of 2019. It weighs in at roughly 6.5 billion times the mass of our Sun, and its horizon carries a radius of around 120 astronomical units, larger than the entire orbit of Pluto around our own Sun. You are falling toward it. Nothing dramatic is happening around you. There is no membrane to feel, no shimmer in the light, no visible boundary of any kind. Your instruments register nothing unusual whatsoever, because there is nothing unusual there for them to register. The curvature right at the horizon of an object this enormous is actually gentler than the ordinary tidal stress you experience simply standing on the surface of the Earth right now. You would feel no jolt, no sudden pressure, no perceptible transition of any kind. You would cross the single most consequential boundary in the entire universe, and have absolutely no way of ever knowing that you had. The only way to detect it at all would be to try to leave afterward and discover that every direction you attempt to steer toward, including the exact direction you originally came from, now leads only deeper in. Two further strange properties fall directly out of defining a boundary purely by its future. The first is that tidal forces right at the horizon actually get gentler as the black hole itself grows larger, falling off with the square of its total mass. For a black hole only a few times the mass of our Sun, you would be torn apart long before ever reaching the horizon. For something the size of M87, you would cross without feeling a single thing. The larger and more consequential the object, the less it ever announces its own presence. The second property is stranger still, because since the horizon is defined entirely by what will never manage to escape, its exact position depends on things that haven't even happened yet. Drop an enormous load of matter into a black hole tomorrow, and the horizon as it existed today was already, in a very real retrospective sense, slightly larger than it appeared to be at the time. The boundary has, in a genuine technical sense, already quietly accounted for its own future. It was never a local object to begin with. It's a fact about the entire causal structure of spacetime, only ever readable after everything relevant has already happened. The most famous edge in the entire universe, then, is made of absolutely nothing, cannot be detected in any way by anyone actually crossing it, and its precise location depends on events that have not even occurred yet. That is exactly what a boundary looks like when it is built purely out of causal relations and nothing else at all. Which brings us directly to the question that has been quietly waiting since the very start of tonight. If the causal structure really is the fundamental thing, laid out as a fixed pattern of relations spanning the whole of history, then in what sense, if any, does anything actually happen at all? Part 10. The block and the letter. If the causal order really is what's fundamental, then the picture that naturally follows from it is a static one. The reasoning is short. If every single event already has its fixed place within a fixed pattern of relations, this one before that one, this one forever unreachable from that one, then the pattern itself is the reality. And a pattern doesn't happen. It simply is, laid out complete, all of it at once, with no single part of it any more real or any more present than any other part. The entire history of the universe, from whatever counts as its beginning through to whatever counts as its end, exists as one single four-dimensional structure. Every moment of your entire life sitting permanently at its own fixed coordinates. This is what's known as the block universe, and it is very much not a fringe position in physics. It's a view held by a great many working physicists, and the argument for it comes straight out of relativity itself. The reasoning runs like this. Relativity tells us there is no universal present no single privileged way of slicing the universe into everything happening right now. Different observers slice it up differently, and none of them is objectively correct over the others. So consider some event that you personally would call part of your future, and that some other observer, moving relative to you, would call part of their present. If we agree that whatever is present is genuinely real, then that particular event is real for them. And reality isn't the kind of thing that can be true for one person and false for another standing right next to them. So it has to be real for you too, even though, from where you're standing, it still lies in your own future. Wim Reetdijk in 1966 and Hilary Putnam in 1967 independently turned this observation into an explicit formal argument that relativity entails the reality of all times at once past, present and future, all equally existing, with now being nothing more than a convenient label attached to whichever particular slice you personally happen to be occupying. Penrose gave the argument a form you can actually picture, and it involves two ordinary people on a pavement. Two pedestrians pass each other walking in opposite directions at perfectly ordinary walking speed, nothing exotic about it at all. No spaceships required. Simply because they are in relative motion to one another, their respective planes of simultaneity, their two separate definitions of what counts as everything happening right now across the entire universe, are tilted with respect to one another by an almost impossibly small angle. But a small angle, extended out far enough, eventually becomes a very large separation. Extend those two planes all the way out to the Andromeda Galaxy, some 2.5 million light-years distant. And that tiny original tilt has spread out into a difference of an entire day or more. One pedestrian's now already includes some event out at Andromeda that the other pedestrian's now still places firmly in the future. If there happened to be a fleet stationed at Andromeda deciding, at that very moment, whether to launch, one pedestrian would correctly say the decision has already been made and the launch is already underway, while the other would correctly say the decision hasn't been made at all yet and could still go either way. They are standing close enough to each other to bump shoulders in passing. Neither one of them is wrong. And there is no third, more privileged observer anywhere who possesses the actually correct answer, because there simply is no correct answer to be had. That scenario doesn't, by itself, prove anything conclusively, and any honest account has to say so plainly. No signal is actually passing between the two events. Neither pedestrian is learning anything real about Andromeda in that moment. The entire disagreement concerns nothing more than a labelling applied to distant events, rather than anything either one of them could ever act upon. But the pressure this puts on the whole idea of a universal, objective, shared present is entirely real, and it has never gone away in the decades since. The single best-known statement of the block universe view isn't found in any scientific paper at all. It's in a letter. In March of 1955, Einstein learned that his close friend Michel Besso had died. Besso had been his closest confidant since their earliest student days together in Zurich, the very man Einstein had personally thanked in his original 1905 relativity paper. The one person he had discussed the hardest and most difficult problems with for over 50 consecutive years. Einstein wrote to Besso's grieving family, and in that letter he set down the sentence that gets quoted more often today than almost anything else he ever said. For us believing physicists, he wrote, the distinction between past, present, and future is only a stubbornly persistent illusion. He was 76 years old at the time. He died himself barely a month later. Hermann Weyl had said something remarkably similar if considerably more clinically, a few years earlier still. The objective world, Whale wrote, simply is. It does not happen, only to the gaze of consciousness. Crawling upward along the world line of some particular body, does a section of that world come alive as a fleeting image in space, one that appears to continuously change as it moves through time. Take the block picture seriously for just a moment, because it deserves to be genuinely felt, not merely understood on paper. If it's correct, then nothing you have ever lived through has actually been lost. Every single moment you've ever experienced is still sitting there, permanently, at its own fixed coordinates, every bit as real as this exact moment is right now. The people you have lost in your life are still located somewhere within the structure of reality, not gone in the sense of having vanished entirely, but positioned at particular fixed coordinates in a fixed four-dimensional pattern, still permanently doing whatever it was they were doing at that time. And you cannot reach any of it. For the exact same underlying reason, you can never reach a space-like separated event. Not because it no longer exists somewhere, because no path leads there from where you now stand. Nothing about your own world line can ever be steered toward those particular coordinates. The block universe, read this way, is not really a comfort at all. It's an extraordinarily precise description of loss. Everything preserved, permanently, and yet nothing ever accessible again. Now, several honest qualifications are worth making here, because this is exactly the kind of place where physics regularly gets oversold. The block universe is a picture, not a proven theorem. Relativity proves conclusively that there is no universal shared present moment. It does not, on its own, prove that the future exists in exactly the same sense the past does. Those genuinely are two separate claims. And getting from the first one to the second requires additional philosophical premises that not everyone in the field actually accepts. There are serious alternatives that still take relativity fully seriously. The growing block view holds that the past and the present both exist, while the future does not yet, with reality steadily accumulating as new events come into being, preserving a genuine sense of becoming while giving up the notion that the leading edge of that becoming has to form a single shared global surface. Presentism, the view that only the present moment is real at all, is considerably harder to reconcile with relativity, since it requires a preferred slicing of space-time that the theory itself gives you no way to actually identify. It's also worth being clear about what the block picture does not settle, since online discussion tends to be far more confident about this than it should be. It does not, on its own, disprove free will in any sense. The relationship between determinism and human agency is a question that predates modern physics by well over 2,000 years. And nothing about a four-dimensional geometric structure resolves it definitively in either direction. Anyone who tells you relativity has settled that particular question is simply reporting their own philosophical preference and attaching a famous physicist's name to it after the fact. And there is one genuinely awkward observational fact that relationalists tend to point toward. Our actual universe does, in practice, hand us a distinguished frame after all the specific frame in which the cosmic microwave background, the leftover radiation from the early universe, looks statistically identical in every direction. We happen to be moving relative to that background at roughly 370 kilometers per second, and that motion shows up as a measurable lopsidedness across the microwave sky, one that has been measured with very high precision. This isn't a fundamental structural feature built into space-time itself. It's a contingent fact, about how matter happens to be distributed throughout the actual universe we live in. But it does mean that in the real, physical universe, unlike in some idealized textbook version of it, there genuinely is a slicing of time that is more natural in a practical sense than all the others. Even Einstein's own position on all of this was less settled than the Besso letter might suggest at first glance. The philosopher Rudolf Carnap recorded a conversation in which Einstein confessed that the experience of now genuinely troubled him deeply, that it clearly means something essential to human beings, something fundamentally different from either the past or the future, and yet that this crucial difference simply does not and cannot occur anywhere within physics itself. Carnap's account has Einstein ultimately concluding that this was a matter of painful but entirely unavoidable resignation, and there was one particular person who took the block picture completely seriously, agreed with it fully, and then turned around and used it as a weapon. He handed his version of the argument to Einstein as a birthday present. Part 11. The birthday present. Kurt Gödel and Albert Einstein walked home together almost every single day. They were both based at the Institute for Advanced Study in Princeton, and by the 1940s the two men had grown close in a way that genuinely surprised the people around them, since neither one of them was, by most accounts, easy company. Einstein is said to have remarked, in his final years, that his own work no longer meant a great deal to him, and that he mainly kept coming into the institute at all for the simple privilege of walking home afterward with Gödel. Gödel was, by any reasonable measure, the greatest logician since Aristotle. He had proven, back in 1931, that any formal mathematical system rich enough to describe basic arithmetic necessarily contains true statements it can never actually prove from within itself. A single result that quietly closed off an entire ambitious program mathematicians had spent decades labouring to build. He was also, by this later point in his life, increasingly fragile, deeply solitary, and possessed of one particular habit that everyone around him noticed. Whenever he became genuinely interested in some subject, he would learn it completely, from the ground up, and then reliably locate the exact thing inside it that everyone else had somehow managed to overlook entirely. Sometime during the 1940s, at Princeton, he became interested in general relativity. For Einstein's 70th birthday, in March of 1949, Gödel gave him an actual solution to his own field equations. The solution describes a universe filled with uniformly distributed dust, rotating steadily rather than expanding, and carrying a negative cosmological constant. It is a perfectly legitimate solution in every mathematical sense. The equations are satisfied exactly, the underlying mathematics is entirely sound, and it doesn't require anything physically absurd like negative mass to make it work. It's simply a universe that general relativity itself fully permits, if perhaps ours isn't actually built that way. Its defining feature is the rotation, and what that rotation ends up doing to the light cones scattered throughout it. In Gödel's universe, the ongoing rotation progressively tips the cones further and further the farther you move away from any given starting point. Near you, the cones stand upright in the usual way, and the future lies straightforwardly ahead, exactly as you'd expect. Farther out, they begin to lean. Farther still, they lean even more. And beyond a certain critical distance, they have tipped over so far that the very direction we would normally call into the future has swung fully around to now point partly back the way you originally came, in time as well as in space. The consequence of this is that you could, in principle, leave from any given event, always travelling locally into your own personal future the entire way, never doing anything remotely strange, never once exceeding the speed of light, never violating a single local law of physics anywhere along the route, and eventually arrive back at the very same event you originally started from. Not back at the same location at some later point in time, back at the exact same event, your own past, with an earlier version of yourself already standing right there, about to leave. Through every single event in Gödel's rotating universe, such a path genuinely exists, not in some exotic corner of it. Everywhere, Gödel's real point in constructing all of this, though, was never really about whether time travel might actually be possible. He wasn't especially interested in travel itself as a topic. His point was philosophical, and he laid it out clearly in a companion essay published alongside the mathematical solution. In his particular universe, he argued, there is no such thing as an objective lapse of time at all. There couldn't possibly be, because a genuine lapse of time requires that the universe be sliceable into a coherent sequence of successive moments, one after another, and in his cosmos, any attempt at such a slicing eventually runs headlong into its own past and closes into a loop. No consistent global ordering of moments can exist there at all. So in that particular universe, time does not pass in any objective sense whatsoever. And here is Gödel's actual move. If there exist physically possible worlds in which time simply does not objectively pass, and if our own world differs from those worlds only in the purely contingent details of exactly how its matter happens to be arranged and distributed, then the passage of time itself cannot be an essential, built-in feature of reality at large. It cannot be woven into the fundamental structure of things as such. At most, it's a local accident of our particular arrangement, and more likely still, it's something we ourselves are quietly contributing to the picture rather than something reality is handing to us. Gödel had taken relativity, the very theory that made space-time into a genuine physical object in its own right, and used the theory's own built-in permissiveness to argue that the flow of time isn't actually part of the world at all. Einstein's own published response is worth reading closely, precisely because of its evident discomfort. He acknowledged plainly that Gödel's solutions were fully mathematically consistent, described them as an important contribution to the field, and noted that they raised a question that had already quietly disturbed him personally, all the way back at the time general relativity itself was first being written. He then suggested, without a great deal of real conviction behind it, that solutions of this particular kind might eventually have to be excluded on some additional physical grounds not currently included in the theory. They have never actually been excluded. Nothing anywhere within general relativity, as it currently stands, forbids paths that loop back and close on themselves. They show up in other legitimate solutions too, not just Gödel's. Inside the ring-shaped singularity found at the heart of a rotating black hole, around certain, idealized, infinitely long rotating cylinders, within the geometries associated with theoretically traversable wormholes. Whatever ultimately rules such loops out, if anything genuinely does, is not something written into the theory as originally formulated. It has to be added in separately by hand, in the form of additional assumptions about which kinds of matter and which kinds of overall global structure actually count as physically reasonable. The standard objection at this point is the one almost everyone instinctively reaches for. Surely a closed loop in time inevitably produces some kind of logical contradiction, someone travelling back and somehow preventing their own original departure. And surely any genuine contradiction rules the whole scenario out entirely. The standard reply found in the actual literature is considerably more subtle than that, and considerably more unsettling. It's called the self-consistency principle, and it holds that only globally consistent histories are ever permitted to occur in the first place. If you travel around such a loop, whatever you end up doing on the far side of it was already, from the very beginning, part of the exact history that led you there in the first place. Nothing is ever actually changed, because there was never some alternate version of events in which things unfolded any differently. The loop isn't a paradox at all. It's simply a history that happens to be shaped like a circle, and any traveller's apparent freedom to act within it is quietly constrained by the strict requirement that the circle must ultimately close. Whether that counts as a genuine resolution or as a clever evasion probably depends mostly on how deeply uncomfortable you find the underlying answer. The closed time-like curves found deep inside a rotating black hole are worth a sentence of their own here, since they represent the most concrete real-world case of all this. The exact mathematical solution describing a spinning black hole contains deep within it a region surrounding the ring-shaped singularity where loops of exactly this kind genuinely exist. Almost certainly, this particular region is never actually physically realized in nature. A real astrophysical collapse doesn't produce the fully idealized eternal version of this geometry, and the inner structure involved is generally believed to be unstable in any case. But the underlying fact still stands. The standard mathematical solution describing the single most common variety of black hole found throughout the universe genuinely contains, somewhere deep within it, a place where time closes back in on itself. Our own universe, it's worth being clear, is not Gödel's universe. Ours is expanding, which his explicitly is not, and the current observational limits on any overall rotation of the entire cosmos are extraordinarily tight, far tighter than his particular solution would actually require to apply here. Actually, travelling along one of his closed loops would demand sustained speeds above roughly 70% of the speed of light, and a journey covering something on the order of 100 billion light years, which is simply a technical way of saying that these curves genuinely exist within the geometry and remain thoroughly hopeless in any practical sense. But the underlying principle still stands, and it remains genuinely uncomfortable to sit with. The single most thoroughly confirmed theory of space and time that we currently possess does not, entirely on its own, guarantee that causes must always precede their own effects. That guarantee, the strict acyclic condition, the very thing the causal set program has to simply assume as an unproven axiom from the outset. The thing this entire night has been quietly treating as absolute bedrock the whole way through is not something general relativity actually hands you for free. It's something physicists still have to hope for. In 1992, Hawking proposed a possible way to plug this exact gap. He called it the chronology protection conjecture, the idea that whenever any region of spacetime is on the verge of developing closed time-like curves, quantum effects will inevitably intervene and prevent it from happening. The vacuum energy of quantum fields would diverge sharply as the loop attempted to close, destroying the surrounding geometry entirely before the loop could ever actually form. The evidence supporting it remains suggestive rather than genuinely conclusive, and a full, rigorous proof would require a complete working theory of quantum gravity, which happens to be exactly the thing nobody currently has in hand. Hawking closed the paper with a line that has considerably outlived the specific argument surrounding it. The conjecture, he wrote, makes the universe safe for historians. It remains, to this day, nothing more than a conjecture. And the theory that would ultimately settle the question once, and for all the one that would finally combine quantum mechanics with the full geometry of spacetime, turns out to carry an even more immediate and pressing problem with time built directly into it. Because when physicists finally sat down and actually wrote out the quantum equation for the entire universe, the resulting equation contained no time in it whatsoever. So here is where tonight leaves you. Underneath every sunrise you've ever watched, underneath every hand you've ever held, there was never a stage waiting patiently to hold it all. There were only ever events, and the quiet, patient relations between them, one thing reaching another, across a structure that has been counting itself into existence since before there was anyone alive to notice. Somewhere above you right now, the light cones are leaning ever so slightly toward the mass of the earth beneath you, and whatever comes next for you tonight is already being decided by that tilt. Nothing is holding this structure up from underneath. Nothing needs to. It isn't resting on anything at all. It is what everything else has been quietly resting on the whole time. If tonight helped you drift somewhere calmer than where you started, let the channel keep doing that for you. Subscribe and come back tomorrow night for the next quiet question the universe has been waiting patiently for someone to ask.